Hi everyone. So we have another interesting talk today about constructing maps with hidden attractors. This is a very interesting result. It's a variation on the technique that I have probably uploaded in a previous video. By the way, all of these techniques and videos on chaos are on a separate playlist in my channel. So if you want to see all the videos about chaos and chaotification and applications, go to the playlists and you will find everything combined. So we are going to discuss about a paper from a publication in Symmetry, a very recent publication. It's called the family of 1D chaotic maps without equilibria. So again, we are talking about discrete time systems. And basically, this work falls under the scope of chaotification, okay? Let me remind everybody, I have discussed this in a previous video as well. The idea behind chaotification is this. Basically, since there are already many maps existing in the literature, there is no point in making a work on just one new chaotic map. Since there are so many works, a much better design perspective is to have a general technique that can use any existing map from the literature. This is the small f that we have here. So we can take as a seed the logistic map, the sign map, the Renwi map, the Chebyshev map, the tent map, any other map from the literature, and design a new map that has, generally speaking, richer behavior. And by richer, of course, I mean we may achieve robust chaos, we may achieve absence of equilibria, we may achieve a higher Lyapunov exponent, we may achieve control of the statistical properties of the map, we may achieve coexisting attractors, we may achieve offset boosting. So depending on our specific goals, we may want to achieve a better behavior in the system, but not for just a single map. We ideally want to achieve this for any possible map that we use as a seed. Okay, so we're practically trying to design families of new systems. Okay, now in this specific paper, we work on designing maps with hidden attractors. Hidden attractors means that we want to have systems that don't have equilibria. Okay, geometrically speaking, in the phase diagram, this means that we don't have any intersection with a bisector. Okay, in the graph right here. And we do this by designing a new family of piecewise maps that have two subfunctions, two pieces, if you like, each one described by a function f1 and f2. And the idea is this, you can actually see the visual representation. We take any of these original functions f1 and f2, and we rescale them and remap them in such a way that the left function f1 lies above the bisector and the right function f2 lies below the bisector. You can see it visually here. On the left, we have the original graph of a function. F1 and F2 are the red and blue curves right here. Basically, this is a scaled version of the logistic map. And what we do is we rescale the red part so that it lies above the bisector, and we rescale the blue part so that it lies below the bisector. So basically, with this rescaling and refactoring, and translating, because this is how it's called, the moving curve translation, we can manage to achieve a family of functions and a family of maps that don't have any equilibria. So basically, this means that any period one behavior is completely destroyed. Okay, and we test this technique using several different functions f1 and f2. Let me give you some examples. The most basic example that we have is, of course, the use of a polynomial function. Polynomial functions are very common, of course, in chaotic maps. So we have here a power of d in the first and the second subfunction. And yet, as you can see in the graph here, we have polynomial curves, and for different parameter values, both the left and the right subfunction are both, the one is above, the other is below the bisector. So here, any map that we obtain has no equilibria. So period one behavior is destroyed, and any attractor that exists is a hidden attractor. Okay. You will see actually from the graph of Lyapunov exponents, here the color represents positive Lyapunov exponent value, and any black areas that you see for different parameter pairs means that we have periodicity. Okay, so we don't manage to achieve robust chaos. In the previous videos that I have uploaded, in other chaotification techniques, we achieved robust chaos. Here we achieve hidden attractors, but we don't achieve robustness. Unless we count some very small sub-regions in the state space where actually we do have robust chaos, but the region is much smaller. So here you will see other interesting phenomena appearing. you will see that we have very dense transitions in and out of chaos as the parameters vary. Here we have this sort of fractal self-similarity in these regions. You will see that these dense transitions in and out of chaos are self-similar, which is a very interesting phenomenon. It also appears on the right graph as well. And you can see that we have some sort of symmetry between the parameters. On the left graph, we have a symmetry with respect to the, not with the bisector, with the anti-diagonal in the graph. In the right, we have some symmetry with respect to the diagonal of the graph. So this is a very interesting phenomenon. You will see that this map has a very rich behavior. We have very dense transitions in and out of chaos, which is a statement about its behavior being very, very, very complex. Another map that we have tried is using a different seed function consisting of trigonometric terms. So here you will see we use the cosine function. So you will see the curve is a bit different in shape, but again, with appropriate values of A, B, and C, we managed to achieve one part of the curve above the bisector, the second part of the curve below the bisector. So these maps again have no equilibria. Okay. Again, we see very dense transitions in and out of chaos. The left graph is relatively similar to the previous one. The right one is a bit different. We have big ranges of periodicity, but other ranges have rich behavior, very chaotic, but of course we have dense transitions in and out of chaos. So the regions of robust chaos are much, much, much smaller, compared at least with the previous videos that I have, where we achieve chaos through and through. Okay, so again, a very rich behavior in the system. And I have one more example, which is a bit more complex. In the previous two examples, not the polynomial, I'm sorry, the functions f1 and then f2 that I used were of the same type, both polynomial, both trigonometric. Here I have a variation where the first function is sinusoidal, the second function is exponential. So we have a combination of two different types of functions, okay, trigonometric and exponential. That's why you see in the graph here that the left and right part of the curve have different shapes because the left one is trigonometric, the right one is exponential. Again, of course, we managed to achieve absence of equilibria, so we have hidden attractors. The Lyapunov exponents show again very, very high symmetry. In the left graph is with respect to the anti-diagonal, and in the right, in the left graph, yes, it's with respect to the anti-diagonal. In the right graph, it's with respect to the diagonal. Okay, very dense transitions in the out of chaos. So overall, every map that we considered has a very, very rich behavior. Now, of course, robust chaotic maps are a bit more desired in applications. Here, still we thought we would consider an application to a random bit generator. Of course, prbgs are relevant not just for encryption, but other types of applications as well. For example, path planning or watermarking or whatever. We have this technique right here. Let me move a little bit. This technique uses remainder-based hashing in combination with a decimal to binary conversion. So basically, we take the value of the map and we generate 16 bits in each iteration. And despite the maps that we used not having robust chaos, we tested each of these maps using the NIST statistical tests. And you see that all of the statistical tests are passed successfully. So these maps right here can still be used in applications related to encryption because they give good enough randomness, okay, despite the fact that they don't have robust chaos. Now, as with the previous works, this publication has a lot of potential for different variations and future topics of study. As I told you in any paper, because you have some limited space, we only consider a couple of examples. So there are many more examples that you can consider because this is basically a chaotification technique. So we considered here a polynomial map, trigonometric map, and a trigonometric exponential map. But you can read the paper, which is open access, and you can consider and design any map that you want with many different functions in mind. Of course, another very big topic, I actually mentioned this in other videos as well, is the elimination of any type of period end behavior. This is a much more challenging mathematical problem and a very interesting problem at hand, of course. And if you're interested, you can design fractional order versions of this codification technique. Okay. Now, of course, let me say we talk a lot about prbgs and a lot about encryption, but basically, as you well know, chaos has other applications apart from encryption. So any of the maps that I have in this video and in all of the previous videos, apart from prbg, apart from encryption, you can consider other applications relevant to security. For example, path planning is one of them. Another application is authentication. Another application is watermarking. And you consider optimization is another application, not directly relevant to security, but as an engineering application, it is very, very useful. We have chaotic optimization techniques. So generally speaking, you can consider any other application of this map and for the previous maps as well that I have in previous videos. Okay, so regarding future topics of interest, I would say just be my guest, anything that you can come up with is a potential very interesting topic of study. Okay, so you can read the paper. If you have any questions, feel free to email us. We will be happy to help you understanding our work. And I think I'll see you in later videos.